Hi, everyone. This is the second set of notes for week 3. It has some by hand calculations in it that I would love to see you do along with me. Oh, beep, beep. Sorry, I had it set up for the second portion of the notes and then it wasn't. Confidence intervals. That's the second part of the week. There is some by hand calculation. You'll be learning a formula that you'll need to know for the exam and for the homework. It's not a terrible formula. We'll walk through it. And it's a handy formula because it gives us a different way of estimating the middle portion of your data, particularly estimating true mu. So let's get right to it. So all of week 2 is about how data is sus, right? To use the word the kids are using. Your sample is never going to be perfect. There's always sampling error. Even if you're a conscientious statistician and you're doing your best, there's always going to be sampling error to your data. So what does this mean? You know, we can try to engage in the central limit theorem and collect samples over 30 and cross our fingers and assume that it will be a decent estimate of mu when we have our sample mean. But it's very exceedingly super duper rare that our sample mean is going to be the exact same thing as mu. So that's a very specific estimate of mu, the sample mean. Sometimes it's also referred to the point estimate of mu. You might hear that term out there. But again, that's not going to be a perfect exact replica of true mu. So statisticians have come up with what are called confidence intervals that we use in order to calculate indeed an interval of data in which we believe true mu exists. So if a point estimate is mean, that one number summary of the middle portion of the data where you add together all of your data points and divide by the number of data points that you just added together. Confidence interval is an interval of data in which we believe true mu will exist. So that's a little bit weird. How can I talk about this via metaphor? Let's say you're going to meet a friend for lunch. And let's say you could say to your friend, okay, I'll see you at 12:15. That's like a point estimate. That's like using the mean to describe when you're going to get there. Why do I say that? You're probably going to show up around 12:15, but the chances that you're going to show up exactly at 12:15 on the nose are rare, right? So it's a decent estimate. It's not a terrible estimate. It's going to be around the right number, right? When you're using a sample mean, but it's not going to be exactly the same as mu. So that's like using the mean or the point estimate. But you could also talk to your friend and say, I'll be there between 12:10 and 12:20. In the real world, why would you say this? Maybe, you know, that you always need a bathroom break after your class, or maybe you unexpectedly run into construction, or maybe it's raining between classes. So you're going to like dodge in and out of buildings in order to stay dry, but it'll take you longer to get to the meeting place, right? Life is crazy, as we've learned, and there's any number of reasons that you wouldn't be there exactly on time, but you'll probably be able to make it between 12:10 and 12:20. 12:10 to 12:20 is like the confidence interval. It's less precise. So that's kind of annoying. What if your friend shows up at 12:10 and you don't get there at 12 till 12:20? Like you're still like accurate, right? But you're not very precise, and your friend might be standing there by themselves for 10 minutes, right? And that can be a little annoying. So giving that range of data is less precise, but it's more likely to contain the true time. For example, let's say that you make this plan with your friend and you show up at 12:12. Well, your point estimate's not correct. You got there at 12:12, not 12:15 on the nose. But 12:12 is contained between 12:10 and 12:20. So that less precise way of stating the fact of when you're going to get there, less precise, but it had the actual time you showed up there within your interval. Note the interval, the confidence interval doesn't always contain true mu. Maybe you got there at 12:05 because your class ran short, or maybe you couldn't get there until 12:25 and because you spilled soda all over yourself and you need to go to the bathroom and clean up. I don't know. So again, what am I trying to get at? The point estimate, the mean, isn't a terrible way of summarizing and estimating mu, but it's rarely going to be exactly right. So we came up with confidence intervals. Why? Because no sample is perfect. And your confidence interval, while less precise, is more likely to contain true mean data. It's kind of about giving yourself a little bit of wiggle room, to be honest. Who doesn't love some wiggle room in life, right? No sample is perfect. You're owning up to the fact that your sample isn't perfect. So what would you give to your reader? What would you give to someone? You would say, I collected information on the number of credits Gannon students took during the fall 20 semester. And I could give you the mean number of credits, or I could give you this confidence interval in which I believe TrueMu is going to exist. Why is it called a confidence interval? Stats are about never being sure about anything. Stats are always flawed. Stats always deal with sampling error. So we don't call it the interval of definitely contains the mu or the certainty interval or anything. We're just pretty sure that the interval is going to include true mu. How confident are we typically? We have 90% confidence intervals and 95% confidence intervals. We'll get into that very shortly. In theory, you could have a 60% confidence interval or a 99% confidence interval. But when you state your findings for a confidence interval, like let's say you run a 95% confidence interval, you're saying that you're 95% confident that the true mu is going to be within this data range. And there's 5% error. If you're 90% confident, there's 10% error. Why do we say confident? Because we never can be completely sure we're dealing with flawed data in the first place. How do you calculate a confidence interval? Here is the formula. You will have to do this formula for homework and for the exam. And it's kind of familiar, no need to panic, right? So we have some like old friends here. If you take a look, we have mean. So that's a good one to have. And you have standard error. These are things that you're already familiar with. And you have this new business Z confidence interval. So what are you doing? It's the mean plus or minus the Z score times the standard error. So note the plus or minus sign. So you're going to have basically for your interval, you're going to have the mean plus whatever you come up with when you take the multiplication of standard error times Z, and your mean minus that same number. We'll cover this later on in the chapter, but this portion of your data is actually called margin of error, which is probably something you've heard of before, especially during election season when we talk about polls. We'll talk about that in greater detail shortly. So again, this is the Z-score formula. I have it down here. Caveat, if you have a mu, you can use that, or you can use the mean. If you don't have your sigma, you can use the standard deviation. Either work, depending on whether or not you have population or sample data available. So what is that ZCI? I made up that notation for it's the Z-score that represents the confidence interval that you want to perform. So it's the Z-score that you use to set up that confidence interval you want. So again, typically we're going to do 90 or 95% confidence intervals. That works a little bit better. And the Z-score that you put in that formula we just looked at, this formula right here, you're going to put in a Z-score, and that Z-score is going to allow you to conduct the 90 or 95% confidence interval. And this is kind of similar to the null hypothesis statistical testing that we talked about in the previous video, in that you're going to use the Z-score as kind of a gatekeeper. So what do I mean by a 90% confidence interval? I'm going to estimate 90% of all possible sample means and where I believe that the true mu would exist. And what does that mean? I'm 95% confident that it's going to be there in the middle portion of the data, but I also have 5% on the left and 5% of the right. And I need to find the Z-score that will gate in the middle 90% of my data. Similarly, if I had a 95% confidence interval, my error rate, known as alpha, we'll cover that again, would be 2.5 on either side. This should really remind you of null hypothesis statistical testing, where you have 95% in the middle, 5% in the outermost regions. P is less than 0.05, 0.05. I repeated a lot of times in the last slide, or the last section of notes. So what does this mean? It means that for my confidence interval formula, I need to find the ZCI that would gate in that particular confidence interval, which would be 95%, with 2.5 on either side. So again, I talked about a little bit alpha, Greek letter alpha. Sorry, that weird line shows up sometimes. That's a little bit better. Alpha is the error. So if you have a 95% confidence interval, you're 95% confident that the true mu will be in your interval, but you also have The 5% alpha, which means 5% of the time you're going to be wrong, stated here. Similarly, if you use a 90% confidence interval, that error region is going to be the outermost 10% of your data, like here. So your alpha would be 5 plus 5 is 10. So your alpha associated with any confidence interval is 100 minus your confidence interval. Why? Remember that the normal distribution contains 100% of your data. We talked about that when we talked about the normal curve. Therefore, if confidence interval is 90, the alpha, the amount of time you're going to be wrong, the amount of data and portion of the data that you're not accounting for would be 10%. These are just some vocabulary words. I'm going to bring it all together in a very handwritten slide here in a few minutes. So here is, oh, that shouldn't say that. Should say confidence interval. It shouldn't say square there, demo. Note that the mu isn't always going to be found in your confidence interval, and your interval can just goof up and be wrong. This is a confidence interval demo made by our psychologist, Christopher Magnuson, who is a talented statistician / clinical psychologist / computer programmer. And let's set this up. So here is a slide, and I'm going to change my confidence interval. So I could make it a 95% confidence interval as shown there, or I could make it the broader 90% confidence interval. Or like I stated, 90 and 95 are what are typically used. Those are the conventions, but I could have a 43% confidence interval as well. But let's start with a 95% confidence interval. So for 95% confidence interval, what is being generated here? For the 95% confidence interval, for all samples of size 5, which is a tiny, crappy sample, right? The blue dot represents the sample mean, and the black bar here represents individual confidence intervals, just to make sure that we're on the same page, because this is a useful way of looking at it. So again, for example, like this bar right here is just one confidence interval. So let's say you have this big population of data and you drew a sample of 5 and you created a 95% confidence interval. This black bar represents that one confidence interval. And what do I have going down here with this red slash? That's the sample mean, or true mu. So what is this big busy form showing us? How frequently does any given confidence interval contain true mu? And here we can see that if the confidence interval denoted by this black line overlaps with the red dash, then that means that the confidence interval includes true mu. And it doesn't always happen. Look right there, that red line. They calculated out a confidence interval with some pretend set of data and it didn't contain it. So I'm going to clear all my drawings and resume. And maybe even make it a little bit faster. So again, if we're looking at a 95% confidence interval with sample sizes of 5, most of the time we're going to have true mu included, but not all the time. The red lines like this guy represent a time when confidence interval is not included. So what could I do if I made myself less confident? If I made myself only, let's have it nice and even, a 40% confidence interval, what do we see? What does it do to my data? It doesn't really change my sample means at all. What happens though? My bars get shorter. So when you make a confidence interval smaller, you're casting a more narrow net. Your confidence interval becomes smaller and it's more likely to not contain mu. Why? Because it's smaller, not because it's worse. The math is pretty consistent, but a small confidence interval is less likely to contain true mu. What does help your confidence interval as well? Let's look at this, and if we'll look at the sample size, we get even tighter and tighter into here. So let's say I want my regular 90% confidence interval and I have a big sample size. What do we see here? Boom, look at that gorgeousness. That would make a statistician very happy. You can be fairly certain that your confidence interval is always going to represent mean. All right, enough of that for now. So what's the takeaway from this? just a visual of what it looks like, one representation, but also precision and accuracy. If you make a smaller confidence interval, like that 40% confidence interval, it's more accurate. The confidence interval is going to become more narrow and more precise. However, it's less likely to contain true mu. And that's the big trade-off with confidence intervals. If you have a broader confidence interval, you're more confident, 95% confident versus 90% confident. However, the more narrow you go, the less likely you are to contain true mu. Okay, so jumping around here. So this is our confidence interval formula. Let me erase all the ink on that slide. So this is my formula, M plus a z-score times standard error. You know what a mean is, you know what standard error is. So we talked about that z-score business. I talked about how you need to find a z subscript ci that represents the confidence interval you're selecting. Typically, that's going to be a 90 or 95% confidence interval. So what does that mean? When you get around to doing the formula, which again is mean plus or minus ZCI times sigma over root n, this ZCI is going to typically be 1.96 or 1.645. Why? Those z-scores are the z-scores that either capture the middle 90% of your data or the middle 95% of your data. So what do I mean by that? Here are little snippets of your good old z-table, right? Spend a lot of time on the z-table. If you want a 90% confidence interval, you need to find z-scores at which you have 90% in the middle, which means you need 5% to the right and 5% to the left. Well, where is that? When are we going to have an area beyond the z that's 5% to the right and left? It's right between the z-score of 1.645 and 1.65. So the z-score that you will plug and chug away if I ask you for a 90% confidence interval is going to be 1.645. Likewise, if I ask you for a 95% confidence interval, you need to find 95 in the middle and 2.5 here and 2.5 here because it's a nice mirror symmetrical distribution. What do you need? You need z-scores that will capture the middle 95% of the data and have 2.5% in the most extreme portion. If you look up a z-score of 1.96, the area beyond the z is 0.025 or 2.5%. So at 1.96 or negative 1.96, you would have the z-scores that would capture the middle 95%. Likewise, if I had 1.645 negative and 1.645, sorry about these weird lines, you would have the z-scores that would capture the middle portion, which is still a little confusing. So here's my attempt at kind of bringing it all together here. So let's say that you are, not everything is there. Okay, this doesn't have exactly everything I had on the first draft. I'll correct it though. So let's say I'm looking at a confidence interval that's 90%. My alpha is going to be 10%. So what does that mean? I want a normal curve with 90% of my data in the middle and 5% on either side. The z-score that corresponds to that z-score that captures the middle portion of my data would be a z-score of negative 1.645 and positive 1.645. So when I do my confidence interval formula for that z subscript ci, I would put in 1.645. And I can correct this and it works out just fine. So let's say I'm doing a 95% confidence interval. So what would I say there? Sorry. If I want to be 95% confident that my true mu is going to be found in my confidence interval, I set my confidence interval at 95%. My alpha would be 5%, which means I'm going to capture the middle 95% of my data and the outermost 5% of my data. Per the z-table I showed you on the previous slide, that is going to be a 1.96. So what does that mean for my formula? It means that I would plug and chug away with 1.96 as my z-score that represents the confidence interval of my choice, which is 95%. This will make further sense as we go along because we're going to work through an example. So let's say that your confidence interval has to do with laptop stickers. So lots of people like to personalize their laptops. They like to kind of show the world themselves, or maybe they just like to amuse themselves. They enjoy the aesthetics of a pretty stickered laptop. So let's say you're gathering data on the number of laptop students have, number of stickers students have on their laptops at Gannon. And you collect a little sample of 33 people and you find a mean of 6.2 with a standard deviation of 5.8. So that's fairly big, right? As a standard deviation, if the mean's only 6.2, right? There's plenty of people that don't have any stickers at all. And let's say I want to calculate out the confidence interval for my 95%. So sometimes it's a little bit easier if you work with this where you kind of pull out the data that you're going to need. So here's my mean and standard deviation. I have my n size, which I'm going to need, and my 1.96 is my z confidence interval that I'm going to plug and chug away. So here is the formula, and here's what it would turn into if I put in all of the particular data from this, right? My mean is 6.2 stickers, plus or minus my ZCI, which is 1.96. My standard deviation from my sample, because you could use a standard deviation or a sigma, depending on what you have. That standard deviation will be 5.8 and your Z or your n size is 33. So I did this step by step so people wouldn't get confused at all. So if you have a standard error, right, figure out that square root and then do 5.8 divided by 5.74 to get your 1.01. Then what do? You would take 1.01, which again is your standard error, and multiply it by your z-score of 1.96. Which gives you 1.98, which again, this is sometimes called margin of error, as I mentioned before. So what do you believe the true mu is for all Gannon stickers and all Gannon students and all of their laptop stickers? 6.2 stickers plus or minus 1.98 stickers. No, you don't have 1.98 of a sticker, but mathematically that's the number that you got. How could you state this in your words? That is found right here. I'm 95% confident that the true population mean is between 4.22 and 8.18 stickers. What did I do here? Sometimes with confidence intervals, you can use this format or you just use the plus or minus. Sometimes you also can use this format where you actually do the adding and subtracting to create the actual interval. It'll be clear what's required of you when you do the exam and when you do the quiz, but both formats are sharing the same thing. So before we get any further, I want to show you a video about some information on confidence intervals in the real world, and confidence intervals being used to help people make really, really important decisions. And in this situation, what are we talking about? We're going to talk about medical professionals who, I'm sorry, I just wanted to share screen under ideal conditions for you. Medical professionals who are trying to help worried, frightened parents make really good choices about their children's healthcare. In particular, using confidence intervals without ever saying confidence intervals in order to help explain medical data to parents. Why didn't they use the term medical or the confidence interval, the Stancy words? If you're trying to make a decision about your kid's heart surgery, you really don't have time for a stats lesson. So what did these people from England do in order to discuss heart surgery rates? Watch as they describe confidence intervals without ever saying it in this video. The predicted range is really a
To understand how a hospital is doing, we calculate the hospital's survival rate and compare this to its predicted range of survival. If the hospital is doing as predicted, then we expect the survival rate to be within the predicted range nearly all of the time. But how is the predicted range of survival calculated? We look at the children the hospital has treated. To make the numbers easy, let's suppose that the hospital has done exactly 100 heart operations. The NHS collects data on all children who have surgery, which includes things like age, weight.
So NHS is National Health Service, which is the way medicine is organized and distributed in the UK.
Diagnosis, difficulty of the proposed surgery, and complicating conditions. All of these factors can affect a child's chances of survival. A statistical formula weighs up these factors for each child and calculates a chance of survival. We do this for all the children that the hospital treated. We cannot predict exactly what will happen to these children, and sadly, it is very unlikely that they will all survive. A plausible way for things to turn out is that 2 don't survive, giving an overall 98% survival rate. Given all the chances that have been calculated, another plausible result.
Just to interrupt again. So when we see them talking about all of these possible futures, this should hopefully remind you of the distribution of the sampling mean. What's going on here? They're talking about all of these alternate samples that could have been created depending on how reality played out. So when we talk about sampling distribution or distribution of the sample mean, we're just talking about all possible samples you could have drawn. Similarly, this is a distribution of sample mean, and over here you're going to see them create that sample distribution.
Is that 3 out of these 100 children don't survive, giving a 97% overall survival rate. We can consider lots of other plausible outcomes for these 100 children. We calculate the width of the predicted range so that the overall survival rate for the hospital lies within it 19 times out of 20.
All right, guys, so that's the predicted range. That happens 19 times out of 20. 19 times out of 20 is 5% alpha, 95% confidence interval. So they're talking about a 95% confidence interval. What does the confidence interval measure? All possible outcomes and where they believe the true outcome is going to be 95% of the time.
Given the chances calculated for these children using the formula. Let's watch this in action.
They're drawing their sampling distribution. Distribution of the sampling mean.
We can keep on considering possible outcomes for these 100 children. We calculate the width of this wider interval, the extended predicted range, so that the overall survival rate for the hospital lies within it, 998 times out of 1,000.
So that's a different confidence interval, because remember, you can make any confidence interval you want to. 40% confidence interval, 99.999% confidence interval, and that's pretty much what they've done here.
Again, let's watch this in action. We now have the predicted and extended predicted ranges for the children treated at this hospital. When a hospital does relatively few operations, unforeseeable factors have a bigger influence on the overall survival rate, and so it has a wider predicted range than a hospital that does more operations.
That last bit should also remind you of class, because big samples be good. If you have a smaller sample, you're going to have more random error in it, right? Because standard error is sigma over root n.
The predicted range depends only on the children treated by a hospital. Different hospitals will always have different predicted ranges, since they treat different children. So if one hospital has a lower predicted range than another, it is only because it treated children with more complex medical problems. To read more about the predicted range along with other information.
So I think this example is moving because a statistician's trying to fight the good fight, right? They're trying to help parents make good decisions when they're very afraid. Now, what kind of data are we talking about? This is data. Let's look at all hospitals. That helps. So what have they got here? This is survival rate for heart surgery at a variety of hospitals throughout the UK. Because as a parent, you get to choose where your kid's going to have their surgery. Maybe you choose the best of the best. Maybe you choose a place near where your sister lives, so you have extra support when your child's recovering. Maybe you select the hospital closest to your own home, right? You've got all of these different 95% confidence intervals, right? You have the true survival percent, which is like a sample mean, but the sample mean probably falls somewhere within this interval. And again, if you look at the full scale, you can see that all of these hospitals are doing really well. And a lot of these hospitals have overlapping confidence intervals, right? Why did they create this? I suspect that understandably scared parents who love their children to bits would all want to go to the, I'm sure I'm going to Leicester, maybe. Reminds me of Lancaster. Anyway, so they're going to the Glenfield Hospital. Why? Well, pick the number that's highest. 99.4 is highest. Well, that just happened to be the random sample for a given amount of data with realities that unfolded the way that they did. But if you take a look at the actual confidence intervals, the confidence intervals are overlapping. And when confidence intervals are overlapping, that means the outcomes are actually fairly similar. And in this case, they're really good. I mean, you would want a 100% confidence interval, like, or 100% survival rate, right? For your kid, for yourself. But this is dang close. And this isn't an only way that you sometimes see confidence intervals used in the real world. Confidence intervals actually were part of a Supreme Court death penalty case. And I think this case is interesting in this class T is because it's statistics, but it's also psychology. Why they're looking at estimates of intelligence. So we should preface this story with Atkins versus Virginia, which was a previous Supreme Court case that established that people with severe intellectual disabilities, typically defined as an IQ of 70 or lower, can't be subjected to the death penalty. They can stand trial for their crimes. They can be jailed for life for their crimes. But the argument was made that it is cruel and inhumane to have the ultimate price paid by people who cognitively maybe weren't really able to fully understand what they did. That doesn't mean that they can't be punished. It just means that they can't be murdered by the state. So what came up as a question, should the death penalty exist if one's estimate of IQ, so like their one instance of their IQ being measured, is above the cutoff for severe intellectual ability, but their confidence interval for where their IQ probably is didn't all fall above the IQ of 70 cutoff point. So this was Hall versus Florida, a more recent Supreme Court case. And what was the issue? Hall, who was found guilty for kidnapping, rape, and murder. So not a good person, but that doesn't mean they don't have constitutional rights, right? So the question is in whether or not he was guilty or whether or not he should serve time, right? That's been established by the court over, the crime happened over 20 years ago. And he is in prison paying for his crimes. But the question was, should this person be subjected to the death penalty because of their low IQ? And when they took an IQ test, they got a 71. So that is 1 point above the cutoff, right? However, the confidence interval, the margin of error is plus or minus 5 IQ points. So what did that mean? It's easier with the visual piece. So here is the cutoff point for severe intellectual disability that was established and is used by most states when they're trying to figure out whether or not the death penalty can be applied. And Hall's estimate was 71, but with the plus or minus 5%, his actual confidence in our actual IQ could be anywhere between 66 and 76. Why is there a 5% or 5-point margin of error? The 5-point margin of error is there because, I mean, just think about yourself. Would you rather take an exam for this class with a sinus infection or without a sinus infection? So what do I mean by that? If you have a sinus infection, you're not going to perform as well. And it's not because you were magically made dumb. It's because your face hurts, you're not sleeping well, you're cranky, and that's all going to influence your test performance, even if it doesn't influence your underlying statistical knowledge. You know what I mean? Also, there's a certain amount of objectivity when people score IQ tests. So again, it's not a perfect measure of one's inherent intelligence, but it's the best we've gotten. It has 5% margin of error. So what did Hall's lawyers argue? That you can't just have the firm cutoff of 70. You need other measures of IQ used, and you need to be aware of what margin of error means. And the court actually ruled in favor of Hall. I believe Justice Kennedy wrote the main response to it for in favor of Hall. And again, if you're a Supreme Court nerd, and there are Supreme Court nerds, it might also interest you that the American Psychological Association actually filed an amicus briefing. So what does this mean? The American Psychological Association was heavily involved with this court case, and they actually testified in front of the Supreme Court, and they gave a lot of information. Why? Because psychologists are experts at measuring IQs, and they're dang good at statistics. So they had a lot of to offer to help the Supreme Court and the justices explain all of this. And any day that I feel intimidated as a statistics professor, I remember that I'm not trying to teach Supreme Court justices about statistics, which is what a statistician had to do in this court case. And one last bit on the margin of error, which I already highlighted, but this is the margin of error. It's everything to the right of the plus or minus. And you've probably heard that term before when they've talked about political polling. As I sit here recording this, it is December 2020. So we just went through the Trump-Biden election. So there was all kind of predictive data of people trying to figure out what would be the final vote spread for Biden and Trump. And margin of error comes up a lot when we're talking about polling data accuracy, because no political polling data is ever 100% perfect. And sometimes, like back in the previous election, the Clinton-Trump election, the polls were quite a bit off. So we need to remember that no political poll is perfect if it says someone's going to win by 53%. But what if the margin of error overlaps? That when they talk about the plus or minus, and this is data from The Economist magazine. And to acquaint you with this data, the solid bars are the median estimate from all of these different polls for the final tally and the estimated number of electoral college votes that both Biden and Trump would win. And what I want to highlight here is this is the median, say, for Biden, but in this darker blue, as you can see up here, that's a 60% confidence interval. So they're 60% confident that the true mean for Biden will fall within that dark blue, and they're 95% confident that it'll fall within this light blue region, which definitely overlaps with Trump's. Trump's, again, here's the median score that they calculated based on a bunch of different polls, 60% confidence interval, 60% confident that the true number of electoral college votes would fall within there. And then this light pink, which again, you can see that when the 95% confidence intervals overlap, it's a little hard to see. So this was, again, if you look at the median, it looks like they're really far apart, but when you have overlapping confidence intervals or margin of error, it shows that it's a lot closer than you think. Here, again, it's December 10, 2020, and here are the results for the Electoral College's Electoral College votes based on the Associated Press. Biden with 320 and Trump with 230. Biden was predicted by this to have 356 and Trump 182. So this was off, right? The prediction was off. And over here, I tried to draw little lines based on this y-axis. And this little blue line here is about where 320 would be. And this red line here is around where 232 would be. And what do we see for the Biden prediction? It does fall within the 60% confidence interval. And with the Trump prediction, it falls within the 95% confidence interval. So again, how should you look at pollsters, and how much grief should you give pollsters? Look at the margin of error, look at the confidence interval that they're presenting. Yes, indeed, their main estimates with the median were off, but both estimates contained the 95% confidence interval for the data. I also emphasize this because I want you to be stats literate, and this is part of being stats literate, to understand what it means when we're talking about confidence intervals and margin of error applied to high stake things like presidential elections. And finally, there is extra credit hidden away, not really hidden away. It's in the same folder as this PowerPoint. And that extra credit's a little bit involved, but not impossible. And there's a video of the notes and the instructions. There's a PowerPoint of the instructions, and there's a data set waiting there for you. So good luck with those, and good luck with the extra credit. And again, my extra credits ask you to do stuff you're going to have to do again in the future. And that is what I have for you guys today. Good luck with week 3, and I'll see you for week 4.